Okay, so I'm going to go ahead and get started with 1.2. So now we're going to be starting with our binomial expansion. So a binomial expansion has two terms. So it's either going to be a plus b or a minus b. And then if I were to ask you to do something squared or to the third power, that should be pretty straightforward for you. But what if it gets to the higher powers? That gets more and more frustrating. So for example, let's just look and see if we can figure out a pattern. So first, if we have a plus b to the first power, I know this one seems really straightforward, but we would just have 1a plus 1b, right? Super simple, nothing new. What about a plus b squared? So this is just your standard foiling. So we would have 1a squared, our first term, and then you would have plus ab plus ab. And since those are the same thing, we would have plus 2ab plus, and then our last term would be b times b, which is b squared. For the next one, if we were to have a plus b to the third power, our first one would be 1a cubed plus 3a squared b plus 3b squared a plus 1b cubed. Now you guys could write it out and see that this is the case, but I'm just telling you this is the case for this example. But if you want to pause the video and try it out yourself to make sure that math adds up to you, then you can. And then finally, we have a plus b to the fourth power. And I can tell you now that that is 1a to the fourth plus 4a cubed b to the first power plus 6a squared b squared plus 4a b to the third power plus 1b to the fourth. Now, I know this was a lot of information really quickly. You can practice writing this out. But the first pattern that I notice is that the powers always add up to n. And so what I mean by this is, let's look at that last example. So we have the fourth to the fourth power. That means that every one of these terms will add to 4. So we have 3 plus 1, we have 2 plus 2, and we have 3 plus 1, and then just 4 plus 0, right? And then the other thing that we notice is that every power of a is present from 0 to 1. So what I mean by that is a, we have an a to the fourth power, an a to the third power, a to the second power, and a to the first power. And then also the last one is if there was no a term. So that would be a to the 0 power. So the other thing is that the powers are symmetrical. So for the a powers, we go 4, 3, 2, 1, 0. And for the b powers, we go 0, 1, 2, 3, 4. Therefore, we can use the binomial shortcut. This is why I was able to do it so quickly without writing anything down, is I have a couple of different ways to do it. And we'll get to that in a second, but it can be used to determine the coefficients of just any term. This is what you'll probably see most frequently on the IB exam. So they only want you to find the coefficient of x to the fifth, y to the third in this one. And so what we're going to do is if this is a plus b to the n, what we have is our a is x. Oh, sorry. Okay, so what we have here, how we determine our n and our r. Our n is always this power here. Sorry, my highlighter went away. Our n is always the power. So in this case, it is 8. And then in order to determine which number is our r, since it is a n minus r, our a term is x, so we have x to the fifth. So that would be x to the fifth is the same thing as x to the 8 minus r. So in this case, our r would be 3. So it will also, your r in this case, since they always add up to n, your r will also just be the second term. So if I were to plug this into the formula, I would be left with 8 take 3 times a to the 8 minus 3 times b to the 3. But now we need to talk about finding what this 8 takes 3 means. The fastest way to do this with a small power is Pascal's triangle. I'm going to show you how to do this one. This one is probably a little bit bigger than I would normally use for Pascal's triangle, but I'm going to go ahead and show you how it works anyway. So the way that Pascal's triangle works is that it will follow the same pattern as what we were doing up above. So you always have 1, 1, 1. That's how every Pascal's triangle starts. And so if you look at the first line, you should have 1a plus 1b, and then the second one is 1a plus 2ab plus 1b squared. And the other way that you can determine this is that it will be all ones on the outside edge, but then it will be the sum of the two numbers above it. So for example, our next row would be 1, and then 1 plus 2 is 3, 2 plus 1 is 3, and then a 1 on the outside. Our next row would be sorry, I keep on zooming in with my hand. Sorry, so the next row would be 1, 4, 6, 4, 1. And the next row would be 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and so on, so forth. And I am running out of room, but good thing I'm right here at the end, because our last one is the row that we need. 1, 8. Okay, finally, now that I have this all written out. So when they say 8 take 3, we're going to find the 8th row. So the row that has an 8 as the second number. So this is 8. And then take the third number from that 8. So we have 1, 2, and then 56 is 3. So that tells me that the coefficient is 56. Now, obviously, that took me a while to write out all of Pascal's triangle, and I don't have time to memorize very far into the triangle. And yes, I can write this all out and figure it out during the test, but in terms of time saving, that's not really very helpful. So instead, we use the factorial formula for binomial coefficients. So I will do that over here. So we have n factorial, which would be 8 factorial, over r factorial, which is 3 factorial, times n minus r factorial, which is 8 minus 3, which gives us 5 factorial. Okay, so if you remember, a factorial is where you are multiplying that number times every number that is less than that. So we would have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Divided by 3 factorial, so that would be 3 times 2 times 1 times 5 factorial, which would be times 5 times 4 times 3 times 2 times 1. Okay, so what I would like to point out, obviously, is that this times 5 times 4 times 3 times 2 times 1, or rather 5 factorial, is both in the top and the bottom. So therefore, we don't have to multiply it, we can just cancel it out. Similarly, 3 times 2 times 1 is just 6, which I have up here, so I can cancel those out. And I'm just left with 8 times 7, which we all know to be 56. So if they were asking me to find the coefficient of x to the 5th, y to the 3rd in the expansion, I would be able to say that the coefficient is 56. Either one way of this work would be fine. So one's just clearly much faster than the other, but if it's a low power, you can do Pascal's triangle pretty quickly. Okay, so moving on to the other side of your notes. Okay, so I am really hoping that you guys are familiar with some of scientific notation, and this will just be a review, but a lot of you highlighted it on your syllabus, but I'm hoping it was just the way that it was worded that confused you. So when we're working with things in scientific notation or in the form a times 10 to the k, what we need to focus on first, we'll do adding and subtracting two numbers when they're written in scientific notation. So the first step is to write the number with a smaller exponent so that it has the same exponent as the number with the larger exponent. So in order to do that, we would need to move the decimal to the left. So we are moving the decimal to the left. And then we would add or subtract the decimal numbers. The power of 10 will not change. Okay, so sorry, let me just make sure, just in case, that you know why I'm saying we're moving the decimal place to the left. So if I have, let's look at just this first example, 5.7 times 10 to the 4th. That one is the one with the smaller exponent. In order to move it to the left, I'm saying that this is the same thing as saying 5.7, sorry, excuse me, is the same as saying 0.57 times 10 to the 5th. The reason why we did that is now our bases of times 10 to the 5th are the same. But if you were to put both of those numbers into your calculator, they're the same number. Really, we just moved an extra tens place, which remember if you move a tens place, would now move it back to the right by adding that extra 10th power. So from there, our next step is to add or subtract our decimals. So now I'm just looking at my 4.87 and my 0.57, because those 10 to the fifths, you can almost think of them as, I guess, sort of like a variable almost. So really we're just adding those two things, which we would get 5.44 times 10 to the fifth. And that power stays the same. The only thing you need to check is that it is still in scientific notation, meaning that there's one number and only one number in front of the decimal place. So we only have that 5 in front. It's not 15 or 50. So that means we are good to go. So the next one is subtraction. We're going to follow the same step. I encourage you to just take a second, pause the video, try this one on your own. Okay, now that you've tried it, I am going to write it out. So we have 0.4108 times 10 to the 7th power. We got to make sure that we have those powers the same, minus 2.835 times 10 to the 7th. Okay, which when I subtract those, I'm left with negative 2.4242 times 10 to the 7th. And that is that. Okay, now the steps are not incredibly different when you are doing multiplication and division. So the first thing is just to multiply or divide the decimal numbers. So for this first example, when I multiply them together, I did it on my piece of paper. You can work it out as well. But you should get 21.08. And then you need to multiply or divide the powers of 10 by adding or subtracting their exponents. So if you're multiplying, then you're adding. If you are dividing, then you're subtracting. So in this case, since we're multiplying, we would be adding. So I would do negative 2 plus 6, which is 4. So then now my answer is 21.08 times 10 to the 4th power. Now, again, our last step is to convert it back to scientific notation right now, because that 21.08 it has two numbers in front of the decimal place. That is not correct. So now I need to move the decimal place to the left. If I'm moving the decimal place to the left, then I need to change the power. Sorry, excuse me. So basically what I'm doing is, in order to move that decimal place over, I am dividing by 10, which means I subtract a power. And since I am dividing by 10, I would be left with 2.108 times 10 to the which means I am left with 10 to the 5th power. Similarly, on the second example, if we are working with division, okay, so we would have 4.3 divided by 2, which is 2.15 times 10. And because we're dividing, now we are subtracting. So we would have 9 minus 4, which is 10 to the 5th power. And since this one is in scientific notation, I am good to go.